Hello everyone. So my name is Rajit Tarana, and today we are going to present about our research work which is Unified AI Framework for Predictive Pediatric Healthcare with multilingual and resource limited settings. So my name is Rajit Tarana, and I have another three colleagues, which is Tarim Navaratna, Vicharatna, and Kavinda Kulkuri Surya. So we are from SLIIT Sri Lanka from Department of Software Engineering, and let's talk about the solutions that we have found. So first we talk about the problem statement, which is one thing is that the fragmented data, which is the data analyzed separately. So there are missing interdependencies between data, nutrition data, and behavioral data of the pediatric health. And the next thing is the static nutrition tool. So most of the generic recommendations ignore child dynamic behaviors. So it was another problem. So we were trying to achieve. And other thing is that delayed emergency responses, which is the fragmented system operating independently. So it affects avoidable pediatric mobility and mortality. And also language and accessibility barriers. If you talk about linguistic barriers, exclude vulnerable populations like Sinhala and Tamil populations, or if there are no proficiency in English. So these are the problems that we were trying to address through this research application and combining four AML integrated systems into one tool, so that which is very easy to accessible. So this is a simple system overview diagram. We have a different kind of data inputs and we have different set of outputs. That so basically there are four core components in here, like health predictor analyzer, nutrition optimizer, and emergency risk predictor, and the caregiver support conversation AI. So these are the main core components that provide these kind of set of outputs using different kind of technology. So this is a huge environment, huge system. So we divide it into four components and implement those things and try to test it out with the different algorithms in AI field and deep learning mechanism. So if you talk about my component, which is AI-driven predictive health analytics with multi-domain integration component, so we were there were basically two separate kind of data set, which is one thing is the PIC ICU data set. You can get this data from a permission, and other thing is that we conducted some consent form with the survey to get the cultural specified data to get a good understanding in the Southeast Asian region. Yeah. So if you talk about the model ablation flow chart, one thing is a unified LSTM. Sol unified LSTM were very it was not perfect. Actually, it was very bad. So it was because we try to integrate multi-domain data, which is temporal data, and it can be not normal classifications data, and like nutrition data. Then the growth are very temporal data. So we are trying to integrate different kind of data, the different kind of domains, and try to get a one prediction, one classification like it. So initially, using one LSTM using solely LSTM is a failure. Then we try to use the transfer learning with the LSTM, but it was also a failure, as you can see. So we then, in the end of the research, we found a way to do this using hybrid LSTM architecture, which is there is a one LSTM architecture and another DNN layer. So it can capture the features in the both types of data, which is temporal and the normal horizontal data. So if we talk about the results of this component, these are the results that unified LSTM combined. We got very low, it's and very low map matrices, and the transfer learning is also very bad. So in the final two models, with the separate pipelines, we got 3.18 of map and 0.975 AUC. So our target basically was try to get lower 5% of the map and zero point 0.9 greater AUZ. So we were able to achieve that kind of result with the existing data, but there are limitations. So let's talk about other compounds from the other members and finally.
So let's talk about the second component, the adaptive pediatric nutrition optimization. So let's look at how system work. It's all start with the child profile, capturing health condition, medication, and dietary needs. This profile passed to the Gemini 2.5 flash, a large language model. It's extract structured dietary restriction, clinical data automatic. Before the meal recommendation reached to the caregiver, every food item passed to the 100% allergen and contraindication blocking layer. The Panda Boolean filter hard blocks the clinically unsafe food. Safety is non-negotiable. From there, the system uses stochastic and collaborative filtering based on ranking to score meal across two dimensions. Caloric, caloric precision, minimum variance using a loss function over 15 iteration, and taste preparation matching through the cosine similarity against the child's historical flavor profile. Finally, It's an E-greedy diversity strategy with 50% exploration ensure variety introducing new micronutrition over time the reactive nutrition mandatory. The entire system is backed by multi-dimensional dataset over the thousand Sri Lankan food items encoded and scaled for machine learning. The tech stack is fully decentralized, fast API backend, MongoDB, Atlas, and a React Native mobile frontend, making it deployable and accessible in real-world settings. Looking at the result, we evaluate the system over the 7-day feedback cycle and the number speaker themselves, behavior alignment, how well the meal plans match to each child's real world eating behavior jumped to 0 percentage on day 1 to 89.42 percentage by day 7. That's a near complete alignment achieved under the V. Calories precision improved dynamically well as from the variation to plus minus 165 calories down to the just plus minus 22 kilocalories well within clinical iteration. Critically, we recorded zero allergen and contraindication variation across all test scenarios, 100% safety adherence throughout. The system work is safe, it's personalized, and it's adapts.
Let me walk you through our emergency care and telehealth architecture. The system is built around three main components that work together to support fast and accurate decision making. First, we have the risk assessment and AI triage service. Here, patient data is collected through a mobile front end, including symptoms, vitals, and images. We use a lightweight model, MobileNet V2, for visual triage, combined with physiological scores like PIRS. These are fused together to generate a reliable triage decision with strict confidence threshold to ensure safety. Next is the priority teleconsultation service. Based on the triage result, high-risk patients are automatically prioritized. Doctors can view sorted cases through a dashboard, access reports in advance, and initiate real-time consultation using WebRTC video. This ensures critical patients receive immediate attention without delays. Finally, we have the geospatial hospital routing service. This module finds nearby hospitals based on capabilities, not just distance. It integrates real-time traffic data into estimate travel time accurately and can launch navigation directly for the user. Overall, this architecture ensures a seamless flow from detection to consultation to physical care. Now, looking at the results of our system compared to the EfficientNet V0 baseline, our proposed MobileNet V2 with Fusion approach shows clear improvements. Triage accuracy increased from 83.1% to 87.4%, which is critical for emergency decision making. The PIRS score decreased slightly, indicating more reliable physiological assessment. One of the biggest improvements in isolated image accuracy, which jumped from 20.3% to 66.8%. This shows the strength of combining visual and physiological data instead of relying on images alone. We also reduced inference latency from 144 milliseconds to 95 milliseconds, making the system faster and suitable for real-time use, even on edge devices. In practical terms, users can connect to a doctor in about 1.2 minutes. User satisfaction scores from both caregivers and clinicians are above 80, which is considered good. Overall, these results demonstrate that our system is not only for more accurate but also faster, scalable, and practical for real-world emergency care.
Finally, the last component of our framework is the multilingual conversational AI module. This module focuses on providing multilingual caregiver assistance using AI-powered conversational support. The system was designed to improve accessibility for caregivers in resource-limited environments through Sinhala, Tamil, and English language support. This slide illustrates the architecture of the conversational AI system. The workflow begins with caregiver interaction through the pediatric mobile application using text, voice, or image inputs. The conversational AI engine then processes multilingual requests and generates pediatric guidance responses. The system also integrates medical knowledge supporting using WHO and Sri Lankan healthcare guidelines together with RAC-based knowledge retrieval. Finally, the real-time AI processing layer generates voice responses, health guidance, emergency alert information, and self-care recommendations. Overall, this architecture enables real-time multilingual caregiver support. So, in this slide presents the key outcomes of achieved by conversational AI module. Clinical precision improves from 71.3% into baseline LM to 91.7% using direct enhanced system, achieving a 20.4% improvement. WHO guideline alignment increased from 68.5% to 94.2%. Multilingual accuracy, Sinhala and Tamil, improved from 62.4% to 88.6%, which is 26.2 improvement. In addition, the user satisfaction and other metrics also improved. Another important achievement was achieving these improvements without additional fine-tuning costs through the use of a rack system. So these slides demonstrate how all modules operate together within this unified framework. The workflow begins with when the caregiver opens the application and enters child data. The system then performs growth prediction, generates a personalized meal plan, provides emergency triage support, and finally delivers multilingual voice follow-up support. The comparison table shows several capabilities achieved by this system that were not fully available in prior systems. These include culturally adapted to Sri Lankan growth prediction, pediatric nutrition with behavioral adaptation, integrated emergency triage with teleconsultation and routing, and multilingual support in Sinhala, Tamil, and English. Currently, so now let's talk about limitations and future work. Currently, the dataset is limited to 69 families from a single district, which is not fully representative of Sri Lankan pediatric population. The nutrition module has mainly been evaluated using simulated pediatric profiles, while broader real user validation is still pending. Language support is also currently limited to Sinhala, Tamil, and English. For future work, the roadmap includes scaling the dataset into more families, 500 families, conducting prospective clinical trials, expanding multilingual support to additional Asian languages, and full deployment with scalable evaluation. So now let's talk about what this system achieves. For predictive analysis, the system achieved 3.18 percentage of MAPE and 0.975 AUC and a 99% error reduction. The nutrition optimization module achieved 89.42% behavioral alignment, 80.6 percentage caloric improvement, and zero safety violation. The emergency response module achieved 87.4 personal triage accuracy with 95 millisecond edge latency and SUS scores between 82 and 84. The conversational AI module achieved a 20.4% improvement in clinical precision, 26.2 percentage of multilingual accuracy improvement, and 94.2 percentage WHO guideline alignment. Overall, these results demonstrate the effectiveness of the unified AI health framework for pediatric care in resource limited settings. So that's it for our presentation. Thank you.